So when looking at exponential functions, a special number comes up naturally, and that's the number e. Let's talk a little bit about where e comes from. Now this notation here, it isn't something that's been covered, so if this piece doesn't make sense, I'll kind of give you a breakdown of what this represents. So with that, let's kind of explore this. Something that's at the base of what e represents is this idea of exponents on 1. So let's say I wanted to find 1 to the power of 1, and 1 to the power of 10, and 1 to the power of 1,000, and 1 to the power of 1,000,000. Now, 1 raised to any power is just 1. So with that, nothing real special happens there. It's just this idea that we can plug in these huge exponents, and if 1's the base, then it doesn't change all that much. So now what I'd like us to look at is, what if we added a fraction? So that's what this is representing inside the base here, is 1 plus this fraction. And what if we plug in bigger and bigger numbers for n right there? So like, what if this was 1 plus 1/10 to the 10 power? What if this was 1 plus 1 over 1,000 to the 1,000th power? And then what if we looked at 1 plus 1 over 1,000,000 to the 1,000,000th power? So what I'm looking at here is 1 plus this little tiny bit, and that little bit that's being added on is getting smaller and smaller. It's like this 1 plus 1 over 1,000,000 is ever so slightly larger than 1. It's like 1.0001. And then what I'm doing is raising it to an absolutely massive exponent. So let's look at a calculator and see what happens when we plug in those numbers. So I'm going to do 1 plus 1/10 to the power of 10. So you get this 2.5937. So what if I put some more zeros on there? 2.7048. What if I put some more zeros on there? Alright, 2.7169. What if I put some more zeros? And more zeros. Oops, not there though. In the exponent there. And let's go ahead to 1,000,000. That would be just one more. And what we can see is as this exponent and denominator, as those are growing larger and larger and larger, we go towards this value of 2.71828. And then we have some decimals there. But I could keep putting more zeros on. And we can see those front numbers are staying basically the same. We're still fine-tuning some numbers out at the end there. But in terms of what's close in there, that's what we're seeing where we're getting this number out. And it's 2.7, just about. Or let's even go 2.7183. It's kind of a rounded version of it. So that's what this notation is getting at here. So this is limit notation, and it's just saying as n is going towards infinity. So it's like, this notation really doesn't make sense mathematically, but it's the idea of, what if we had the largest number we could think of in the denominator and the largest number we could think of in the exponent? And what this is representing is 1 plus a teeny tiny bit, because we know what happens when it's equal to 1, it just stays 1. But what if we make it ever so infinitely tiny bit more than 1, and then raise it to an absolutely massive exponent? That's where we get this number out. And it was the mathematician Euler. He claimed it. His last name starts with E, so he said, that's my number. We're calling it E for Euler. So that's where the E comes from, is just a mathematician claimed it, even though this number occurs naturally in the world all over the place. But for our purposes, we'll just have this letter E. It's irrational, so those decimals aren't going to repeat anywhere. It's not this one specific fraction. But this is our estimate here. So what we want to think of is whenever you see the letter E coming up, it's about equal to the number 2.7183. So just like when you see pi, how it's good to think of that in terms of 3.14 or however decimal places you go out with it, same thing with E. It's not a variable. You don't ever solve for E because we already know what it is. It's just instead of trying to write out this number or by approximating by rounding, because that'll introduce a bunch of error, we use the letter E for accuracy. But it comes from this idea of looking at 1 plus a little tiny bit and then rounding, or and then having an exponent that's really big, and it just comes out to this number here. So in terms of a graph, what we can see is that if we're graphing e to the x, so if we have this growth factor of 2.7183, our graph is going to look pretty similar to 2 to the x and 3 to the x, because it's in between there. It's a little bit closer to 3 to the x. So in this graph here, I know there's lots of colors, but in pink we have 3 to the x, and in this light blue we have 2 to the x. So you can see how this darker blue e to the x is between them. So they all go through 0, 1, but then at x equals 1, we're graphing about 2.78 there for our value of e. So in terms of what we've done already with exponential functions, so like solving equations, if we have this base e, then we treat it the same for solving equations. We just want those exponents to equal each other. So we would just be solving 3x plus 1 equals 2 minus x. And then we don't even see e anymore because it was the base. Let's see, I'd add x to both sides, subtract by 1, divide by 4, and x is 1/4. And we can plug that into the calculator. In fact, let's go ahead and do that. So if you're in the if you're using a non-online calculator, like a TI something or other, you should have an E button on your calculator somewhere. So typically it has E with an exponent for it. If you're using the Desmo Scientific Calculator, you just type in the letter E, and you can see it just assumes that we're using the number E. So we'll have 2, and then in an exponent 2 times 1/4 plus 1. So we get out a number. Oop, that plus 1 should be in the exponent. I need some more parentheses to group that. Plus 1. Okay, now it's calculating correctly, and we get 4.4817. Cool. And then we want to see e to the 2 minus 1/4. And I'm getting different numbers out. What did I do? I typed in a 2 instead of a 3 up above here. Luckily, that's easy to fix. There it is. So, the equation's balanced. We solve for x, and it's just with this base e number, which in your calculator, you can just type in with your keyboard. In terms of a graph, so we'll want to keep in mind this kind of basic form of e to the x. What I keep in mind is, at 1, it's that 2.78-ish. At x equals 2, I think it's about 7.3 is where it lands. I mean, it's the equivalent of e squared, so that number would be exactly 7.389. So somewhere around 7.4. So if I wanted to make a sketch of the basic function, just e to t, what I would do is I'd have the point 0, 1, 1, 2.78-ish, and 2, 7.4-ish. So I just grab those points, and then to the left it just gets closer and closer to the x-axis. So this is exponential growth, and it'll go off that way. Now, so that would be just the base function, e to t. What we have here is a reflection across the x-axis. And here, we're multiplying our variable by 1/2, so that's a horizontal stretch by 2. since that's the equivalent of 1/2 times t. So let's go ahead and reflect over x first. So just move our values below the x-axis. Let's see, 1, 2.78, 2, 7.4-ish. And then we're going towards the x-axis, so something like that. And then horizontal stretch by 2. So let's see. So that 0, -1 is going to stay put since that's on the y-axis. So if I go to like 2.78-ish, I have this distance of 1, and I want to double that distance. And at that 7.4, where I have this distance of 2, I want to double that distance. So, and then everything that's near the x-axis, this is all about making this sketch as best you can, and with all of that close to the x-axis, kind of blends together. All right. So that would be our graph for e to the t, but reflected over the x-axis and then stretched horizontally by 2. So when it comes down to it, best thing you can remember with this is that e is a number and it's about 2.7. If you can remember that and that it's not a variable, that will help with a lot of calculations and all sorts of things that we do with e coming up.